Hello, everyone. Hi, Kye. Hi, everyone.
Hey,
How are you doing? First of all, please let us know if you can hear us all right in the chat.
great.
Perfect. Awesome. Thank you. So, welcome, everyone. Please let us know where are you coming from. And oh, perfect. Thank you, everyone. It's always great to see some familiar faces and names here. Welcome. So we'll be starting in about a minute, just waiting for everyone to join. Everyone will receive notifications. Oh, sorry about the echo. Welcome, everyone. I see that we have representations from all continents, like always. So welcome, everyone. Today we'll be focusing on Open RAN, an exciting and fast evolving topic in the telecom world. It's something we've been getting more and more questions about lately, especially around the security parts implications. With me today is Kye Grundy, telecom security expert at P1 Security, who will walk us through the full picture in just about a moment, including some practical insights. And at the end, we will see a demo, so be ready. Before we start, please note that this webinar, as always, is being recorded, so you can rewatch it or share it with your team later. And of course, feel free to drop any questions that you have in this chat, and we will tackle them in the Q&A session at the end. So, Kye, what do you have planned for us today?
Hey everyone, thanks for joining. It's good to see you all. So yeah, we can jump straight into the webinar. I will go ahead and start if everyone's ready. So today we'll look at ORAN, and I've tried my best to keep it short and concise, and I've tried to isolate ORAN topics because sometimes there's a bit of overlap with pre-ORAN and traditional kind of RAN and architectures and vRAN and stuff like this. So we're going to take some ORAN topics and take a look at them, and then maybe in the future we'll do some deep dives into specific topics or maybe introduce other topics. So without further ado. So who am I primarily? Let's start with that. So I am Kye Grundy. Just get my laser pointer on. I'm Kye Grundy, telecom security expert, and I have a background in pen testing 4G, 5G infrastructures, both RAN and core network. And also I have a strong background in the deployment and management of telecoms labs, architecture and infrastructures. So this includes also security testing there as well. And I've also been following the ORAN security topics internally and completing internal security research projects. So that's kind of why I want to discuss ORAN security today. So the agenda today, I will firstly just do the necessary introductions to ORAN for the people in the audience who are not already familiar with ORAN and some of the basics of the ideas behind it. But I'll try not to spend too long here. Then we'll go into the high-level categories. So what actually does ORAN change compared to pre-ORAN, as an example, compared to normal 4G, normal 5G, or even vRAN? And there's a spoiler in the agenda. So some of the areas that we'll look at are open interfaces, the intelligence layers, the supply chain and software security areas. And also, I do want to mention some topics we couldn't actually discuss because there's a lot to look at, and I wanted to keep this webinar as a quick overview where possible. And then I'll try to summarize that. So just to describe some conclusions we can take away. And at the end, there'll be a short demo of an attack, which I discuss at the beginning of the webinar in the open interfaces as an example of what can happen if there's no security mitigations. So let's get into it. So just to quickly introduce ORAN. So really, what is ORAN? So primarily, it's a new approach to building the RAN. So moving away from those proprietary hardware locked-in environments where it was proprietary software, proprietary hardware, into a more interoperable, open, and intelligent environment, one that will be based on cloud infrastructure. So the specifications are overseen and completed by ORAN Alliance, and actually they will specify new interfaces that are actually make these network functions within a RAN open and interoperable, and intelligence layers that can actually take metrics from these RAN components, make some sort of decision on them, and push config changes to those RAN components, either in real time or non-real time, as you may already be aware. And all of this will be based on COTS hardware, so we don't actually need to rely on specific hardware from a given vendor and specific software. So just to mention that O-RAN, they try to utilize existing specifications from 3GPP. I mean, they have to because of the technology they're deploying, and they actually want to complement where they can. So just a quick diagram about how it could look. It's a very high level. So in the past, you would have this proprietary hardware, proprietary software environment where the interfaces would be locked and you could really mix and match. Then after 3GPP release 15, we started to get the ability to split up the baseband. So this would be split up into the DU and CU, and then we would open up with that F1 interface there. And this could also be virtualized, so let's call it virtual disaggregated RAN here. And then O-RAN took these concepts and actually broke that up even more. So, you know, they used the CU-DU split, they added some intelligence there, and they also defined some extra interfaces, which I'll get into later. And also where the interfaces that were already specified, say like from 3GPP, they actually provide specifications to try and encourage interoperability between the traditional vendors. So let's have a look at what really changed with O-RAN. So there's a lot of information here. I've just put an architecture diagram so we can really take a look what changes. So one of the first big changes with O-RAN is all these new interfaces. So let's ignore the ones we already know from 3GPP, like F1 and E1. Let's look at the fronthaul and the E2 and etc. So for example, with O-RAN, we have O2, open fronthaul, O1, R1, Y1, A1, and E2. So there's a lot of new interfaces here. So we will get into them. We will have a look at the message contents and see what new threats they actually introduce. There's also the adoption of the 7.2x split. So whereas in the past we would have this physical layer we would have the physical layer, which is one monolithic block. Now we have split it up, split it down the middle, and now we have part of the physical layer in the DU and part of it in the RU. So this is exclusive to O-RAN, and it would be a threat that is introduced. O-RAN also introduces intelligence layers, so with the SMO, the non-real-time RIC, the near real-time RIC, and also within those platforms we would have rApps, xApps, and also it's possible that there would be the use of AI and machine learning. There would certainly be an increase of multi-vendors. So in the past, we would see one vendor, but now O-RAN will encourage multiple vendors via their defined interfaces and also over the existing 3GPP interfaces where they try to encourage but not redefine. We will see an increase in the use of open source software, so within the RICs and also the O-RAN network functions. It's stated in multiple places in their specifications that they will aim to use open source where possible. There will also be cloud-based deployment, as mentioned, but O-RAN has actually introduced something exclusive here. vRAN, which is, let's call it non-O-RAN for now, does have acceleration, but O-RAN has actually defined an interface in their specifications where a given O-RAN network function vendor can provide an interface that makes it easier for the software developers to actually integrate with accelerator cards within the hardware. And disaggregation is likely, these split the network functions as mentioned. So let's take a look at some of these and in a bit more detail and see what kind of threats they introduce. And at the end, we will see what sort of mitigations have been defined by O-RAN Alliance. So I will start with open interfaces. So let's take a look there. So starting with the open fronthaul, just to show you in an easy to view way. From a physical point of view, you would see a cell site like this, and you would have a radio unit there, and you would have this link down towards the cabinet, or also the RU could be in the same location as this cabinet, and this would be the fronthaul. And O-RAN O-RAN has specified this interface on top of another protocol called eCPRI. An RU can be connected to a DU and also a higher level orchestrator called the SMO in hybrid mode. So that's the links where you could see the open fronthaul. So the open fronthaul is comprised of different planes. We have the C plane. This is the control plane. So this plane is responsible to instruct an RU to actually transmit or receive incoming or outgoing user data which is the IQ samples. We then have the U-plane, which is the U-plane part of the fronthaul. It's based on eCPRI like C-plane, and this handles the IQ samples which are actually user data. So this could be both the 3GPP signaling, so a UE's NAS messages towards the core networker, or even user data, so video streaming, for example. And this plane actually may already be protected by some existing 3GPP requirements in the name of PDCP, and we will take a look at that later on in detail when we get to the user plane. We also have the sync plane. This is based on PTP or sync E, and it will keep the timing of the radio unit in sync, but it really depends on the type of deployment which is being rolled out. And we also, of course, have a management plane, which is to allow the DU or the SMO, as mentioned, to reconfigure the radio unit or even receive notifications from that. So let's look at this in a bit more detail. So C-plane, as mentioned, is for the control information for the radio unit. And it's actually the way it's been specified by ORAN is they take an existing protocol called eCPRI as an encapsulate. You could see it as like an envelope, and then ORAN Alliance actually defines the real-time control data which is put inside of there. In the past, pre-ORAN, this payload part, so the control data, would be defined by a proprietary vendor, for example. And yeah, it would just be information which we wouldn't really understand. So if you were to take a radio unit and plug it into a distributed unit, a DU, maybe they wouldn't work together because the actual control data is proprietary. It's not openly defined. So what's the security footprint of this in comparison to before? So the fact that we've moved from CPRI to eCPRI. CPRI was sorry, one second. CPRI used to be a time division multiplex protocol, so it wasn't packet-based, whereas eCPRI has moved to a packet-based protocol. So this will be a more familiar environment for malicious actors. The eCPRI header itself also contains various parameters that are sensitive enough to potentially enable a denial of service or even user reconnaissance. So there's a specific field within eCPRI here, which corresponds a given user, so given control or user information to a given DU port, RU port, or even band sector. So it takes a lot of work, but it could be possible. And if there is malicious access to this link, a given attacker, they could insert invalid C-plane messages, and actually the RU would try to execute some sort of transmission or reception of user data, which is incorrect. So this is the demo which I will show later, where we actually crash an emulated radio unit. And also, one point to mention is the fronthaul, as shown in the previous slide, can be deployed at cell sites where there's a lack of physical security. And as mentioned, it may have a link to the higher layer SMO, the orchestrator layers. So this could be a point of pivot within the network. Let's say you walk up to a cell site, which is it doesn't have the same level of security in some cases as a data center. It could be a valid malicious route into the core of a network. The U-plane has similar characteristics as the C-plane. So it's a more familiar environment, for example, but the responsibilities are a little different. So the U-plane, as mentioned, will transport the user data towards the UE or from the UE, and it's in the form of IQ samples. And with no protections on the U-plane, the actual user data could be monitored and modified. And this does depend on if PDCP is actually active, and 3GPP defines this as optional for integrity and confidentiality, which I will show in a second. But if this protection is not here, we could actually see these IQ samples. We can see them anyway, but if they're protected by PDCP, they would be encrypted and integrity protected. But as mentioned, significant processing work needs to be done to actually extract those valid samples. But just as an example, this is the packet structure of the user plane. And IQ samples may look like this. So it could be this is a representation of user data. And a theoretical scenario could tell us that we take these IQ samples and we could actually convert those, so demodulate them back into bytes, and then we could see some sort of user data. This is very theoretical, and in a real scenario, this is highly complex and unlikely, but there's still a possibility of this. We also have the S-plane. So as mentioned, it provides timing to the radio units, and if the timing is actually degraded, the RU would lose its timing and thus its ability to serve UEs who are connected to that cell. So, for example, in a cell, if you have thousands of UEs connected in a really dense area, that would be a lot of denial of service for a lot of users. So this would cause quite the impact in reputation and a lot of negative publicity here. So this is an interface that we really need to protect. So here we see different architectures of timing. I'm not going to go into them all, but it just shows that depending on how timing is deployed, it would provide different types of access to malicious actors. And finally, on the fronthaul, we have the M-plane. So this M-plane, it allows management type actions over the radio unit, and these are usually FCAP type management. So this could be software upgrades, networking reconfiguration, interface reconfiguration, for example, and this can be from the DU or the SMO. So the security controls are defined and they're actually mandatory, which is great, which I will summarize in a later slide. But of course, they need to be implemented correctly and with best practices. If not, it's as good as not having them there, or even it could be cause further problems. So if the protection is not there and it's not really implemented well, the management messages or the notifications would be able to be monitored, modified, or anything else. And because it's configuration management, there can be really targeted attacks here. So if you have a given configuration for a radio unit, i.e. it will find its DU at this address, or we can roll back to a vulnerable piece of firmware on the radio unit, this can be done. And as mentioned, it can be a pivot point into the higher layers, such as the SMO, from a cell site which it doesn't have a lot of physical security. And I've just put a quick example of the different YANG modules. So these YANG modules really define what can be done towards a given radio unit. But we won't get into all of them, but just wanted to point out that there's a lot there. We also have the E2 interface. So E2 interface between the near real-time RIC and the OCU or the ODU actually allows the near real-time RIC and thus xApps to take in real-time metrics from the E2 nodes and use those to formulate some sort of real-time actions over those network functions. And what an actual xApp can do against a given E2 node, so a RAN function, network function, is determined by something called an E2 service model. And I will show you that in a second. And these messages can actually be, they will contain sensitive information, and it can be on a RAN, cell, or even a UE basis. So it's pretty serious that we protect this. And consider that the actual software components making these decisions and receiving this data are from third parties, or maybe from third parties. And also the RIC platforms themselves will be from third parties. So we are really putting a lot of trust in these xApps and RIC platforms to make decisions over the RAN. Each of these components will have their own dependencies, their own access levels, their own code qualities. So we're really expanding the threat surface there. And without adequate security controls, the actual message contents with these on this E2 interface, such as the RAN metrics or configuration data on a UE basis even, can be monitored or modified. And similar to the M-plane, because it's configuration management and it allows configuration of the RAN components, we could really do targeted or sophisticated attacks here. I just wanted to include some example parameters which would be included on the E2 interface. So there's different service models. So for example, KPM, which is a service model for E2 nodes to send KPI metrics to the xApps within the near real-time RIC. We can have UE IDs, beam IDs, or cell global IDs, and actually the corresponding measurement values. With CCC, this is a E2SM for cell configuration and control. And in this service model, on the E2 interface, we may see, for example, XN or X2 hand over allow block lists, cell IDs, tracking areas, so quite sensitive information. And actually, you can maliciously reconfigure these parameters using the E2 interface if there's a compromise. So this is pretty serious. And there's also RC, which is rank control. And this includes tags, serving cells, UEIDs, and also 2 important points to mention. We can actually use this to gather the UE context and also receive copies of RRC messaging. So there's some information here that we wouldn't really want to lose and expose to attackers. Just put an example here of a potential control of the RAN control or the CCC, which allows us to hand over a UE or or UEs to a given target cell. So yeah, that's just an example. Then moving on to O1. The O1 is between O1 nodes, so ODU, OCU, and RICs, and the SMO, the management type services, such as configuration or notifications. So the O1 configuration management is based on netconf, and this is a predefined protocol which already exists. But ORAN have actually defined their own YANG models to describe what can be done in terms of management and notifications. So more so for configuration management, what can be done towards given ORAN network functions. So for example, the ODU may have a YANG model which allows the SMO to reconfigure the fronthaul interface, but the OCU wouldn't have that because it doesn't have that interface, just as a quick example. There's also O1 notifications, and they are delivered over HTTP, and majority of them are actually based on existing 3GPP specifications. So just to group them, the 3GPP defined notifications would be something like this: provisioning management, fault supervision, and also trace management notifications. ORAN has defined their own set of notifications, which is PNF registration, and this actually aids in the ORAN, one of ORAN's use cases of zero-touch provisioning of network functions. So like the other interfaces, if there's no adequate security controls here, we can see and we can monitor and reconfigure or maliciously change the O1 configuration and notification data. And again, this will open the door for sophisticated attacks. We can reconfigure the RAN to really specific targeted attacks. Yeah. And also, the 3GPP defined notifications can be monitored, so such as tracing, which provides tracing on UEs or cells or given subscribers' actions or what they're doing on the network. And also, yeah, we can see some configuration data as mentioned. So I just wanted to add an example of a netconf message towards the radio unit, which actually allows the SMO to reconfigure parameters related to the U plane on the radio unit. Let's look at A1. So A1 is between the near real-time RIC and the non-real-time RIC, and it allows the non-real-time RIC and the near real-time RIC to communicate, to share, it allows the non-real-time RIC to assist the near real-time RIC in its real-time decision-making. And this is done in 3 ways. So primarily, there's A1 policies, and the A1 policies allow the non-real-time RIC to actually send A1 policies to the near real-time RIC. And what policies do, they will say to a near real-time RIC, for example, for a given cell, let's say cell number 1, we want it to be below 70% load. And if the near real-time RIC notices that it's not meeting that policy, it will route to a specific xApp and then make an xApp, reconfigure the RAN. And this is usually the way it works. We also have enrichment information. So this allows non-real-time RIC to send extra information to the near real-time RIC to assist it to make real-time decisions. And it's usually information it doesn't have itself. So for example, geolocation of UEs, which the non-real-time RIC or the SMO layers may have, and they will be able to provide this to the near real-time RIC. Just as an example use case, if the near real-time RIC needed to, let's say, hand over a given UE to another cell to reduce load, maybe knowing the geolocation of a UE, for example, its trajectory and where it's headed, would help and assist to allow the near real-time RIC to make better decisions on how to hand over a given UE, as an example. And there's also A1ML, which allows some sort of AI machine learning exchanges between the 2 RICs. So this is like models and different various training messages. And as the others, if there's weak security controls here or none, we could monitor these A1 messages and also modify them. So if we was to modify a policy maliciously, we could make the near real-time RIC and xApps take actions over the RAN, which are actually undesired and not wanted. And consider again that these xApps, and also rApps within the non-real-time RIC, which are able to invoke A1 services, are from third parties. So we're giving third-party suppliers quite a lot of trust here to take rather drastic decisions over the functioning of the RAN and UEs at that. So this information over A1, it could include UE IDs, cell IDs, geolocations of connected subscribers, as well as the corresponding policies for those identifiers. So just as an example, for A1 policies, the kind of parameters we could expect is UE IDs, slice IDs, cell IDs, and also objectives relating to that. So let's say we have a given UE, we could see the objectives which are assigned to that UE, or even a given cell as the use case I mentioned before. And the A1 enrichment information, what's defined for this so far is the geolocation of UEs. So we would have the timestamp, the UE ID itself, and the actual geolocation. So we could get a correlation between the geolocation of a UE and also the time it was there, which wouldn't be great for connected subscribers if malicious actors had access to this information. So let's look at R1. I believe this is the last interface we would look at now. There's a few we have left out, but let's just dive into this. So R1, it allows rApps in the non-real-time RIC to communicate with the non-real-time RIC platform itself. So the rApps are actually able to invoke services like O1 or open fronthaul services. For the management plane, as mentioned, it can connect to the SMO. And the non-real-time RIC, well, not the non-real-time RIC, it connects to the SMO, which the rApps have access into. The rApps can also provide and generate A1 policies towards the near real-time RIC, and also have access to O2 interfaces within the SMO platform. So if you think about this for a second, these rApps, which are provided by third parties, have access to a whole lot of functionality over an all-RAN system. So we really need to look at how this interface is protected. And as mentioned, they have a lot of responsibility. They have access to information coming in from RAN network functions on subscribers, on UEs, on a cell basis, and they can use that information to make decisions. So they have access to quite a lot of information. And if used maliciously, there could be drastic consequences. So as mentioned, rApps can be provided by third-party vendors who have their own dependencies, have their own access levels, their own code quality, and we do expand the threat surface here. And yeah, as mentioned, if there's weak security controls on the R1 interface, we can monitor this data coming into the rApps over the R1 interface up towards the SMO, the configuration changes, and also even malicious targeted reconfiguration could be performed. You know, we could deploy malicious backdoors by software upgrades, or we could even force shut down cells, for example. So you'll be happy to hear I've finished flying through the interfaces pretty quickly. I actually have to leave some out in the interest of time, but let's quickly look at the summary of the protection. So there was a lot of information I just gave you. What I want to say is you don't need to remember every piece of information on each and every interface. Just consider it from this point of view. There's a lot of new interfaces with a lot of new functionality and a lot of new parameters. So we are expanding the threat surface in various points of the network here. So let's look at the protections what O-RAN Alliance have defined within their requirements. So in this first group, these are the interfaces that have TLS protection for their security control defined, and also OAuth2 for authorization or NACM. So for example, O1 is the only difference here. It would use NACM for the netconf access control model, which the principle there is that for the netconf operations which are possible, we give the least access to the operations or to the network functions which it's facing. And the others are OAuth2, as you may be familiar from the 5G core network for the SBA, for example. We use TLS on all of them for integrity, confidentiality, and authentication. But I want to point you to this key here. So these are shell support. So if you read the specs within the requirements, you will see that these controls, these security controls, are shell support. So we'll get into that a bit later, what that may mean in reality. I also wanted to point out the O2 and Y1 interfaces. I didn't discuss them today, just in the interest of time. But we may do future webinars which gets more into detail of the various interfaces, like I've done today. So there's also E2, which is a difference here. So this is protected by IPsec for integrity, confidentiality, and authentication. And there's a bit of a hole here with E2. There is no authorization defined for the E2 interface. And working group 11, so the working group in O-RAN who is responsible for security have actually said this is an item which is under study and will be defined in the future possibly. Then we have the open fronthaul. So the open fronthaul is a bit different. So we reference its security controls at the network level as well as the interface level. So let's just look at mPlane first. So mPlane at the network level will be protected by 8021X or MACsec or MACsec. And yeah, this is optional support. There will also be mandatory to use. So we know that operators will actually have to use TLS and SSH-v2 for mPlane at the interface level. For the control user and sync plane, it's the same. So it's 8021X and MACsec, which is at the network level. And I want to point out that 8021X and MACsec are optional support, so the vendor doesn't actually have to implement this in software. They don't have to provide this functionality to the operators. But I do want to make a point that authentication at the network level in the specifications is mandatory to do. So we know there will be some sort of authentication at the network level on the fronthaul. It's just not necessary that we would be using 8021X for that. So that summarizes the open interface protections, and I will move on to the next category. So we have, let's look at the intelligence layer security. Yeah. So the intelligence impact on security. So let's look at this from a non-technical point of view at as high level as possible. So we have intelligence layers within the ORAN system that are able to retrieve information from the RAN, real-time and non-real-time. And based on that information, they will be enabled to push configuration changes towards RAN network functions. And where do xApps and rApps know, how do they know what to do to a given RAN? And this is provided from a RAN intent, which is a high-level objective-based messages from the MNO, which says to an SMO, for example, I want the RAN to have this kind of performance. And this will trickle down through the intelligence layers. So xApps and rApps are able to intelligently make decisions to reach this RAN intent. There's also configuration management towards many different vendors. So you have different xApps, different rApps, different intelligence layer supporting platforms, different ORAN network functions. All of this configuration management they're pushing, it's more complex than before. There's different vendors with different requirements on referencing objects within their running software, their running environment, needing different levels of access requirements, for example, and also having more vendors means more suppliers, more third-party personnel who may need access to this equipment. The xApps and rApps, plus the RIC platforms, as mentioned, can be provided by several third-party vendors with their own security practices. And can we trust those third-party vendors? What if the xApps or rApps are compromised and act maliciously? Are they able to access RIC databases that contains UEs, sensitive data, or even cell-level sensitive data? And also the intelligence layers, they link to external entities, which I will show shortly. So how can we verify those external entities? And a lot of the times we cannot do that. So there's an argument to be had if, for example, the owner of the ORAN system also owns that external infrastructure, but we need to consider it as an external entity outside of the ORAN architecture. And as mentioned, the use of open source software will be adopted where appropriate. So let's just take a visual look at the near-real-time RIC and xApps for some of the kind of theoretical threats that can happen. So at the xApp level, we may have malicious or compromised xApps. So what if an xApp is onboarded legitimately and it's a legitimate xApp, it behaves as expected, and actually it's compromised due to a vulnerability? What can it actually do? It has access to the whole RIC platform, possibly, and also the databases, and it can also push malicious changes towards subscribers or even run the cell level. So xApps can also conflict. So what if there's two xApps trying to do the same action? We would have adverse actions taken towards the RAN. xApps may also not be isolated, so it would starve the resources of another xApp. And also we need to consider the fact that maybe untrusted xApps may be onboarded. Also, within the near-real-time RIC, we have an API enablement platform, which needs to make sure that any component, be that RIC platform components or xApps, should be authenticated and authorized, and if not, they would be able to access the whole range of services within the RIC. So we also have external interfaces towards the near-real-time RIC. We have E2, Y1, O1, and A1, as previously mentioned. And each of these need to be treated as what if the peer becomes malicious or is malicious? What can they actually do towards the near-real-time RIC? And as mentioned, we have databases which contain UE level information and also cell level information. We need to protect that database and to protect against information disclosure. Let's move on quickly. So now I will show you near-real-time RIC threats as I've just shown you, and also the non-real-time RIC threats with rApps and SMO. At the end of this, I will show you some mitigations, what can actually be proposed and what have been defined to mitigate these. So I won't go over rApps again because I already mentioned those with xApps, so they're the same. let's look at some specifics to non-real-time RIC. So the non-real-time RIC will also have a service based in the decoupled SMO, for example, or the non-real-time RIC. We would have this messaging infrastructure where the rApps and also functions within the non-real-time RIC or SMO can speak to each other. And we need to make sure that all these services authenticate their peer and also authorize for given services what they expose. So, for example, rApps using this messaging infrastructure can reach out to O2 interfaces, to O2 peers, O1 peers, or even radio units using OFH termination within the SMO. So rApps have quite a lot of power here, and also the other functions within the RIC platform. So we need to make sure that this is protected. We also have external terminations from the non-real-time RIC. It's defined within the specifications. So as mentioned before, when we have an external entity, we can't really verify the security of that as well as the ORAN system. So we should consider that as a threat in its own right. And also non-real-time RIC has data management and exposure. So we could see this similar to the near real-time RIC, where there's some sort of data being stored from the non-real-time metrics and the non-real-time configurations. And actually, we need to protect that data. Non-real-time RIC also has an A1 interface. So again, we need to be sure that the near real-time RIC, which is connected to the non-real-time RIC, isn't malicious and acting as not expected. Okay, so those are the non-real-time RIC threats. Let's look at the SMO. So there's this. So non-real-time RIC is within the SMO, and it would have access to the SMO services, and likewise SMO to non-real-time RIC services. So there can be attacks in and out of non-real-time RIC and SMO, so originating from SMO and also originating from non-real-time RIC. So we need to consider that as a threat in itself as well. Also, SMO has malicious. It has external terminations for interfaces. So any of these peers could become malicious, and we need to keep that in mind. There's also AI machine learning functionality within the SMO. So what if we have an AI-enabled ORAN system? What if that AI data is poisoned and the SMO is starting to push decisions based on data that is not correct? We also have SME and DME within SMO, and I just want to make a point of this. This is an external functionality, so it allows the SMO to expose its services externally. And what this means is SME allows the SMO to expose its services to an external peer. So any of these services you see within the SMO, maybe they could be exposed to an external. There's also DME, which is data management and data management exposure. So it allows the SMO to expose its data externally to peers as well. So this is quite serious, and we need to keep an eye on this to make sure that it's not maliciously used or abused in some way. So I've just said a lot of threats, and a lot of them are theoretical. But let's take a look at some of the requirements that are defined by ORAN Alliance to see what can be done to mitigate against these. So starting with the API, so just to go back quickly, for both the non-real-time RIC and the near real-time RIC, we had API infrastructure. So let's look at that first. So I'm going to break it up into RICs and also the SMO. So for the near real-time RIC, it is mandated to support. So notice that mandated to support, not mandated to do or mandated to use. It's mandated to support authentication, integrity, and confidentiality using mutual TLS, and also a new authorization part, OAuth 2, for the APIs within the near real-time RIC. And for the E2 based APIs, it's the same but using IPsec. So for the non-real-time RIC and SMO, we have the same for the API infrastructure there as well. So it's mandated to support authentication, integrity, and confidentiality with TLS, and also OAuth 2 for the authorization. So I just wanted to point out here, it's mandated to support. So it doesn't mean that it will be done, but it's a positive note that another clause within the spec actually says mandated to authenticate. So we know that an operator or someone who deploys ORAN infrastructure will have to authenticate in some way based on the spec if they're following it completely. And this will be between API producer and consumer. So just as a real example, this could be an rApp with a given service within the non-real-time RIC or SMO. So let's move to database protections. As we saw in the near real-time RIC and at the SMO and non-real-time RIC, there are some sort of databases which store data on UEs or cells. So within the near real-time RIC, we shall authenticate and provide authorized xApp access to the databases within the near real-time RIC. So this is mandatory, so we need to do this. And this is great because we know that that database within the near real-time RIC can hold sensitive UE information or cell level information. So if any xApp from a third party wants to collect this data, they need to first authenticate themselves and also authorize for a given action on that database. On the non-real-time RIC and SMO, there's no real clear requirement for database protection, because if you look at the actual specification for the SMO, there's not a clear function which says database. But we can be confident that actual rApp access is authenticated. So any rApps within the SMO or within the non-real-time RIC would actually have to authenticate to access databases or any other peer who is on that R1 interface. So that's rApps and also non-real-time RIC functionality, so the platform services. And within the SMO, the components within there, they're mandated to support authentication, integrity, and confidentiality with MTLS, and also authorization using OAuth 2. So the database access will be maybe protected this way, implicitly by other protections, but there's no explicit mention of the actual protection there. So that's just a point I wanted to make from the requirements. So let's look at the xApp and rApp protections. So for xApps, it's mandatory for them to be associated with authentication credentials with their unique identifier. So if an xApp is to authenticate within the near real-time RIC platform, it needs to authenticate itself using its own unique identifier. And it's mandatory for communication between xApps and the actual framework to be mutually authenticated, which is great. This is not mandatory to support, it's mandatory to do it, which I will show in more detail later. And also these xApp IDs should have adequate uniqueness. So what that means is, let's say we have a malicious xApp or some sort of malicious actor within the near real-time RIC, it cannot spoof a given xApp to potentially gain its level of access that it has within the near real-time RIC. With rApps, so it's a similar story. It's mandatory for those to provide authorization to the non-real-time RIC framework, and they should be able to recover from malicious intent. And similar to the same as xApps, they should have the IDs used for authorization and authentication should have adequate uniqueness. Let's look at the external peering protections within the intelligence layers. The near real-time RIC. I've not mentioned the Y1 interface, but the near real-time RIC may have a Y1 interface present, and this interface is used for the near real-time RIC to communicate with an external peer to share run metrics in the real time. So again, this is an external peer, so we cannot really guarantee its security posture, but we can do something at the interface level to protect it. And yeah, as discussed, there's support for TLS and OAuth 2, as mentioned in the previous slide. So within the non-real-time RIC and SMO, so SMO external interfaces like DME and SME are mandated to support MTLS for authorization, confidentiality, and integrity protections, as well as OAuth 2 for authorization. So that was just a quick fly through. Just finally, on the intelligence protections, let's quickly look at AI and machine learning. And for all of the protections I've mentioned so far, I've not actually listed all the requirements you will see in the specs, because there would be tons of slides with this information. So I just took a subset of them. I recommend if you want to find out all of the requirements, I would point you towards this specification. So let's look at what they have defined. So access to the models, the AI models, should be authenticated and authorized. The systems controlling that access should enforce the least access control policies that make sure that whoever's consuming it doesn't have too much access. And the models themselves should be integrity and confidentiality protected, both at rest, in use, and transit. And data used or produced by AI model training should be protected in terms of integrity and confidentiality. So we have you can get the picture from this. There's tons more requirements, but just to give you an idea of what that could be. So that was the intelligence layer protections. It was a lot of information. So I'll give you a few seconds to digest that. And we will be moving on to supply chain and software security now. So this will concern both closed source software and also open source software, and the supply chain, and also how we can verify open source software. So let's take a look at that. So we'll start with open source software security. So as I've mentioned, ORAN wants to use open source where possible. And of course, this will introduce various threats. So I took some from OWASP as an example, not all of them. So if there's any vulnerabilities in the open source packages, it will be known because it's public. We can see what packages open source projects use for their functionality. So whereas we have closed source, maybe the dependencies are not as well known in the public. So this is something to keep a note of. And also, we could have a compromise of a legitimate open source package. Open source projects tend to sometimes struggle with funding. So let's say an operator or a given network function vendor decides to use an open source project that becomes unmaintained and a vulnerability is found. How will it be fixed? And will it be fixed at all? So this is a risk with open source. And also, some open source projects would not track their dependencies as well as they should. So this is also a risk. If there's vulnerabilities and you're not aware that you're impacted by it, this can cause problems. So there is an initiative called OpenSSF. And this initiative has been defined, has been started to actually address some of the risks that are present against open source software. And it's maintained by Linux Foundation. And they actually do deliver some projects and some packages that will assist in securing open source software packages. So one deliverable they produce is this open source software project security baseline, which is a minimum set of requirements that an open source project can follow to make sure that it complies with some sort of security requirements, some sort of security standards and best practices. They also provide an automated tool to check for software issues within open source projects. They provide a SIG store, which is a free sign-in verification for software releases, which I will mention in the next slides. And there's also SBOM, which is quite a big topic within ORAN. And the acronym stands for Software Bill of Materials. And it basically means that for every software package that is delivered, both closed source and open source, in fact, has to list clearly what the dependencies are. So if there's ever any vulnerabilities discovered, the MNO or the vendor will be aware that they are impacted by this. So let's look at some of the requirements that ORAN lists for open source software. So as mentioned, we have the SBOM. So for every network function that is provided by a vendor, they will have to create and supply a SBOM for every release with a minimum set of data. So ORAN says in the requirements, when you deliver a piece of software or a given network function, you have to provide an SBOM, and it has to have a specific set of information. If not, it doesn't comply with the requirements. And SBOM, the SBOM itself should be protected. And also OpenSSF, as I mentioned, it's mentioned in various places within specifications, particularly the neurotime RIC and xApp specifications. And there are recommendations made, which are not hard requirements, but it's still recommendations to look at. So, for example, with the RIC platforms and the xApps or rApps, an open source, an inventory, a clean inventory needs to be maintained and kept, which records the open source components and dependencies that are present. We also need to keep a track and analyze the vulnerabilities which arise from the use of various dependencies and open source packages. And we need to continuously monitor for risk to open source. And we need to follow OpenSSF security best practices for ORAN network functions. And I just wanted to point out that there's an ORAN software community, which they actually provide and develop open source reference implementations of ORAN network functions. And these repositories themselves, these projects are actually following the OpenSSF best practices. So this is a good indication that ORAN is taking open source security seriously, that they're actually making the effort to certify their own deliverables within the open source community. Let's look at software package security. So this covers open source and closed source. So these slides will describe when a network function vendor provides a software package, how can we verify that this software package is legitimate and we can trust it? So it can be complex, even more complex than normal, because as mentioned, ORAN would have many different vendors now. And as already said multiple times, they will have their own dependencies, potential vulnerabilities, levels of access. So we really need to make sure that we have a good way to check on this. So let's look at the requirements for this. So the application package itself, so application package here refers to an ORAN network function, could be a CU, a DU, any RIC component, for example, xApps. So before it's delivered to the MNO, it actually has to be certified by the vendor itself. So this could be, for example, via internal pen testing, as an example. And when they provide the package, they shall include the signing certificate and the signatures. So we can verify it from where we believe it to be from, where it should be from. And each application should be digitally signed by the vendor. I will describe this in the next slide in a bit more detail. And as mentioned, SBOM, it needs to be provided for every software package, and the requirements are as shared in the previous slide. And as before with the other requirements I've mentioned, these are a subset of them. So if you want to see the complete list, I would recommend looking at the requirement specification itself. So let's take a look at what the process looks like when a software package is actually delivered into the ORAN system. So let's say we have a network function vendor. They have a software package. What they will do, they will hash this software package, encrypt that with their private key, and form a digital signature. So when the application provider, so the vendor, wants to send this to the MNO, they would take their software package, the digital signature, and their certificate, and send this to the MNO together. When the MNO receives this package, they will check the certificate, they will check the root certificate authority within there, and if it's trusted, they will then say, okay, we know the network function vendor is who they say they are. We know that the public key we received to decrypt the digital signature is theirs. So we decrypt that signature, and then we compare it with our own computation of that signature. And if there's no differences, we are able to see that there's been no modifications and the package is what we expect it to be. And then, of course, we have the software package to do it. This is, of course, simplified. If you want the complete procedure, again, I recommend looking at the requirements specification. But one caveat I wanted to mention is that for this to be successful, the SMO or even any other network function which may onboard software packages within the ORAN system, it would need to have the certificate authority installed so it trusts it when it checks this. And another point I wanted to mention within software security is the zero trust architecture. So this is quite a hot topic within ORAN Working Group 11 at the moment. You can see it in releases on the ORAN website that they're working towards this. And as mentioned, within an ORAN system, we're going to have lots of different vendors, lots of different new components and functionality. So traditional security parameters are no longer suitable here. So we have to trust every piece of communication, even if it's internal to the network. So ORAN is adopting this ideology of zero trust architecture. And the primary idea behind it is that all communication is secured regardless of where it is. So within a network, out of a network, it is treated the same. And accesses are granted on a session basis and on a short-lived basis as well. So we don't provide access for years and forget about it. It's for short periods of time. And also the access that we provide will be continuously monitored. So ORAN Working Group 11 has actually released a technical report on the use of ZTA within the ORAN architecture. So the ORAN Alliance are aiming to reach initial status of ZTA, which I'll show you what that means in a second. ZTA basically has multiple pillars, which describe how advanced you are with your ZTA status. And initially, ORAN is aiming to reach this initial pillar. So you see here, for example, for application access protections, you have the traditional column, and ORAN is aiming to move their ZTA to initial status for various different functions within the ZTA architecture, mapping it to ORAN. They will aim in the future to eventually reach advanced or optimal, but for now they're aiming for initial status in mapping to ZTA. So how does this look in the standards groups? So the way what they're working on really is to check where their gaps are. So they have existing requirements, existing threats, and they're mapping these to zero trust pillars and security requirements. And from this, they will get a gap analysis. So they will see where their requirements don't exactly align with zero trust. From those gaps, they will do a threat analysis. So we have this gap. What is the real threat there? What can be done with this threat? What could a malicious actor do? They will then give it a risk score, and then if needed, they will make updates to their security requirements and controls. And this is a really positive sign. They will try to lock as much as possible and comply as much to zero trust architecture, and they're actively identifying where there would be gaps to try and close those gaps. Okay, so flew over a lot of topics. There was open interfaces, intelligence layers, software package security, and it was still a lot of information. But there was a lot of topics that I wanted to discuss, but I didn't in the interest of time. So let's take a look at some of those. I would recommend to keep an eye out in the future because we will do some releases related to these. So we didn't get to discuss O2 and mobile interfaces in detail. So that will be something for the future. OCloud and virtualization security, we didn't get into this too much. And the reason I didn't include that was because I wanted to isolate ORAN topics themselves. Whereas if I start to discuss virtualization, for example, there's some similarities to vRAN, which can be made, or CRAN. So that's why I left that out for now. And the topics this would be relevant for is VNF security, CNF security, and also acceleration layer from ORAN, which is actually specific to ORAN. So that should be worth a point to discuss in the future. Also, the shared radio unit. This is a topic within ORAN that's exclusive to ORAN. So what are the security impacts of that and what are the controls? So, for example, if we have multiple operators using a given radio unit, would they have some sort of conflicting operations that ruin the service for all their subscribers? Can we trust the users of a radio unit? The potential security impacts of the 7.2x split. There's a more complex radio unit, so the impacts of that need to be addressed. We looked at software package security, but we didn't really look in detail how xApps and rApps get onboarded within the RICs. And there's potentially a hole here within the security requirements, whereby if an xApp is provided by the vendor of the RIC platform, there are security controls defined. But if there's an xApp vendor that isn't the vendor of the RIC platform itself, there are no security controls for that. It is for further study in the requirements. And also, we're speaking about ORAN, but there's non-ORAN issues here. We are still a free GPP infrastructure. We're still using free GPP interfaces, the same physical layer, all but the split. So we still have those same threats and issues. So all I can say is just keep an eye out for future webinars or releases. I'll be certainly attempting to release some research in the future or other webinars, which rather than an overview, gets more into detail into a specific area. So there was a lot of information. I will try my best to make some conclusions or bring us back to the real world. So there has actually been some real vulnerabilities discovered in ORAN network functions. And we can see this with this CVE number and also the P1 vulnerability knowledge base entry, which is a P1 service. So what this is it's a vulnerability with an open source, the Open RAN software community near real-time RIC, whereby an xApp would generate an E2 message towards an E2 node, and internally within the RIC, it would crash because the packet is malformed and not as the specifications have defined. So this actually led to a DOS within the near real-time RIC, DOS of the whole RIC platform. So this is just an example. If these interfaces or xApps are not verified and are not legitimate, they can perform some sort of malicious acts intentionally and cause large-scale crashes within the ORAN system. So what are some key takeaways here? So while support is mandatory, operator use is not mandatory, and that's a really important point. So you'll see within the specs, ORAN have attempted to say to vendors, you need to actually support these security controls, but it's not mandatory to use, not all of them. So what that means is that operators may decide not to actually use those security controls. And if they don't, we're as good as not having them any defined at all. So, and this is not speculation. This is not me theorizing. This is actually within some of the specifications. So within the ZTA specification, there is a clause which states the protocols listed in the table, so the protocols that I've mentioned in the previous slides, they're mandatory for the vendor to support, but they're optional for the operator to use. So that is a pretty important point, that when we get real ORAN deployments, this is something that we need to look out for. And there's a challenge that ORAN specs are constantly moving. There's new releases every 6 months or so. So what if a vendor actually implements or releases a software package that's applicable to a previous ORAN release and thus doesn't have certain security controls, for example? And actually analyzing ORAN security firsthand is quite difficult at the moment because the deployment and uptake of ORAN isn't as quick as maybe some would have imagined or would have liked. So checking and pen testing a real infrastructure is not as where we would want for now. And also, if there is some ORAN infrastructure, maybe they don't actually have the complete feature set. So they wouldn't have all these interfaces and features that I've mentioned. Maybe they would just have a given interface. But the positives, existing tech standards are being used. So ORAN Alliance can actually specify and build upon what already exists. And they are actually mandatory to support, as mentioned. So this is a good thing. I mean, ORAN Alliance are not saying, okay, you can support it if you want, other than the fronthaul requirements, some of them. So that's a good sign. ORAN, they also actually host a vulnerability disclosure platform on their website. So if a vulnerability is found within the ORAN system, it can be published on the ORAN website and they will investigate. This is a good direction. It means that vulnerabilities can be raised towards vendors or standards bodies. And from our point of view, of course, it's recommended to use the defined security controls. ORAN Alliance have made it mandatory for the vendor to support these protocols and these protections. So the functionality is there. So let's use it, right? It's there. There's no excuse to really not use it other than the complexity it takes to implement. And really, a good thing which could be done at the moment is to actually analyze the security posture of a real deployment. So that's when we will really see how the ORAN security stands up to the pre-ORAN deployments. So that's really the main takeaways to try and conclude everything I have discussed. I've put a very quick demo. I know I'm going over time, so apologies for that. But I've included a quick demo. It's only 1 minute long. And what I'm doing here is, so I discussed the fronthaul, so the open fronthaul, the C plane. And what I'm doing, I'm sending malicious open fronthaul C plane messages towards a given radio unit to see what impacts that has on a radio unit. And this is all using open source components. So let's take a look. It's only 50 seconds. So what I will do is start the CU. So you remember that we have the baseband unit, which is CU, DU, and RU, the ORAN architecture. And here I'm using SRS run as the open source project. So I will start the CU. And it sets up the F1 interface for the DU to start. So now I will start the DU. And we'll let that start. And one thing I point out here is that the DU, once it starts, it will initialize that open fronthaul interface towards the radio unit. And it has its connection towards the CU. So now we know the fronthaul interface is up. What we will do, we will start the radio unit emulator. So what this will do, it will wait for C plane messages from a DU to send emulated user plane data and receive it and send it back to the DU. So let's take a look. So, sorry, the video restarted. So once I start this emulator, I will let it start. You'll see that there are some metrics which say received packets on time and transmitted on time. So we know that now it's successfully working. And now I will run the attack code. So let me just slow down a bit. So you see here I'm running a script which actually sends those malicious fronthaul C plane messages towards the emulated radio unit. And you can see here that our emulated radio unit actually crashes because the C plane message it has received from a malicious actor references a subframe index that is not, it doesn't exist, and it's greater than the actual range of subframes that do exist within this environment. So let's try that again. So I'll restart the RU emulator. And this time it will take a bit longer to find the malicious message. So you see successful operation, and then we crash the radio unit again. So this is using an emulated radio unit, which has probably not been battle hardened for deployment, and also it's open source, but it's a real example of if these interfaces are not protected, what can actually happen. So we need to use those security controls. And that is it from me. So yes, thanks for listening. I hope I didn't lose anyone, and I welcome any questions. Thanks.
Thank you so much, Kye, for this amazing and deep dive presentation. Like you said before, this is a very big topic, and it needs a lot of time to deep dive in it. And you mentioned that we might get another ORAN session because 1 hour is definitely not enough. And speaking of which, we also have some webinars coming up, so feel free to respond to this poll and let us know what session you might be interested in. And just to let you take some time, read the questions in the chat. I'll be answering the first question that came about the recording. So in all our sessions, once you register, we always send you the recording after the session ends to your email. And we will also be sharing it in our social media pages on our LinkedIn. It's called P1 Security, and on our website, p1sec.com/webinars on the webinars page. So feel free to join there.
Okay. Should we wait for the poll, or should we jump into the questions?
You can jump into the questions. Okay. Feel free to do so.
So I will go through them. So maybe we don't have time to hit them all, but yeah. So let's start with this one. So which ORAN-defined security measures did you apply in your experiments? So it's a good point. In the open source projects, there is no security measures implemented. So on the open fronthaul, there's no actual required security control implemented there. And this was to mainly illustrate, if we don't have the security control, what can happen. And that was the point there to showcase. And it's really an encouragement to actually implement that security control. I hope that answered the question. Please let me know if not, and I'll try again. So from Ollie, just wanted to note that 8021X support is managed with the ORU, and that is correct. So at the interface level, it's put there as to support. But actually, if we look at the RU spec, to the given features on a given radio unit, an RU vendor will have to support it in case an open fronthaul network or a DU vendor wants to actually implement it or does use it at an MNO perspective. So I'm just looking for other questions. I see. Yeah, so I see one from Rajinder. I think that's a name that I recommend. So, hey, Rajinder. So what is a mechanism for continuous validation of third-party xApps and rApps before and during runtime? So I mentioned one of them, which was for a vendor to actually pen test and verify their package before it is delivered into an MNO. And during runtime, we would encourage that security testing is done, and we take a look at logging. So ORAN specifications actually define that all network functions need to actually support some sort of logging functionality. So we will be able to take a look there as well. And also, as mentioned, xApps actually need to be authenticated and authorized. So if there's any unusual behavior which is there, we would probably be able to protect against it because those requirements are actually mandated. Okay. So I think that's most of the questions. If there are no
definitely. So while you're still checking out, if there are any more questions, you guys feel free to drop any other questions that you have. I know that we passed a little bit of time, so we apologize again about that. Yeah, it's a big topic. And I also sent the contact page link on the chat. So if anyone wants to get more contact with us with P1 Security, feel free to write us on the contact page and we will answer. And you can also click on the button on your screen to book a call directly with us if you want to avoid all the emails. And on your page, you can also see the QR code. So if you scan it, you will find all the future webinars that we have lined up that we showed earlier. We have top 5G security vulnerabilities. We have a telcosec talk coming up. We have a webinar we will be discussing the stage of the telcosec world of this year in 2025. So feel free to register to all of them to get notified. Awesome. So I think there are no more questions, right, Kye?
I don't see any of this.
Oh, awesome. So thank you everyone for coming and for staying with us. It has been a very great and fruitful session. Thanks again, Kye. any last words to close the talk from you, Kye?
Yeah, so as mentioned, I think a good sign up would be that I flew over very quickly a run, an overview, and in the future I would just keep an eye out for any specific topics or any elaborations that I would be outputting.
Awesome.
Thanks
Thank
for
you.
coming along.
Thank you, Kye. And stay tuned, everyone, for any information about what Kye might do in the next sessions. So thank you, everyone. Have a good day, have a good night, have a good morning, depending where you're from. And take care of yourself, and see you next time on the next P1 Security webinar. Goodbye.